It's a good, no great time to be a geologist. Today we talk about why. The answers lie at depth. We're talking energy transition needs, copper getting deeper, smaller, and more expensive to find, geothermal energy, fracking for heat, and creating metamorphic reactions. The answers lie at depth. Depth is the final frontier, and so we need geologists. It's Planet Geo.
And even despite all the beauty rest, this is what we get. I mean, you. What the heck?
Oh man, to get insulted in this way by somebody like you it's more hurtful than it ought to be.
Oh goodness. Today, part 2 in our to be determined series of why it's a good time to be a geologist. Why is this?
Yes.
Why are you excited to be teaching geology to high schoolers?
Mm-hmm.
Why am I? I'm really excited and thrilled to be a geology professor at this current time period in Earth history. Well, not Earth history, human history. I think it's a really important time, and we're going to cover part 2 here. Part 2 is building on
I have a thought.
Where we came from. Yeah,
Chris has a thought.
the first one of the day. Here we go.
Something what you just said is like I am. We've talked about like why you and I got into geoscience because it was just cool. It was a natural attraction to the the power of the earth and the awesomeness of the beauty of it, right? And then wanting to understand all of that and how it all happens. And I still teach that. I still teach that way, but I also am way more deliberate about the practicality of learning about geoscience in a way that 10 years ago I wasn't. It's definitely a different approach that I now have. And I think that a big part of that, Jesse, is because of you and I doing this podcast together.
Well, I have a question for you, Chris, but let me give the pitch in where we're going in this episode. So where we came from, if you haven't listened to our previous episode on this, there are sort of buy low, sell high style of episode that said, basically what we went through in that is that geoscientists are needed at a baseline. So even if the world is not changing underfoot, we're going to need more geologists or more geoscientists in the future just because of the mere fact that there are less being trained, and this is kind of a boom and bust industry, and it has been for the last 50 or 70 years, and we're in one of those lows right now. So it's a good time to go get a geology degree or geoscience degree, we think. What we're going to move into is why we think this next event, the demand is going to grow because the world's changing under our feet. And while a lot of the climate change impacts that we're seeing are at the surface, many of the solutions are at depth. And when you get...
Okay, hold on. We need to double click on that because that's going to actually be like, we're going to title this episode that.
Yeah,
right?
Solutions.
Let's double click because I think it's really important. The problems that we have on Earth are mostly superficial problems. You talk about climate change, transitioning to the green energy, all these different environmental things, water issues and things like this. And then, but the solutions to these problems are at depth. And that's a powerful statement, I think.
I think
I love it.
It makes sense. It makes sense why geoscientists or even traditionally geologists, what we would kind of think of as a geologist, is going to be needed because the solutions are at depth. And we're going to work through kind of that thinking. But Chris, I have a question for you. The summer science course, let's talk about the Summer Science Institute class you've taught for how many years now? 20?
This will be 25. This will be 25.
Ooh,
yes.
What is that? Is that a diamond anniversary? What's 25 here?
Don't know what that's called, but
25, man. Okay, so this class, when I took it, it was you and a biology teacher, high school biology teacher, who ran it. And I think the trip has been going on for before you took it over, and it kind of was biology probably when your dad was teaching it, and it was biology dominated, and then you kind of took over, and geology started to become more of a framework or structurally more important, perhaps.
Yeah, for sure.
Now you teach it with our good buddy Andrew DeWitt, who is in environmental consulting, right? What's the course content? I know he likes to talk about sort of the societal impacts of geoscience on this trip. Has that been a good learning experience for you and for the students?
Absolutely. I think he brings that in, right? He brings in a natural way because for everybody.
And what are some
listening,
examples? Could you just give us like a,
yeah. But Andrew he got his master's degree in geomorphology. So he, you know, so you have
fluvial. We got to make it sound fancier. Fluvial geomorphology.
That's right. I'm a fluvial geomorphologist.
Yeah, that's right. With the head bob, exactly.
He does. He gets really uppity about that. But and so you know, we have two geoscientists that are running the program, and so it's evolved that way for sure. Now Andrew brings in the practical side of a geoscience degree, because that's what he does on a day-to-day basis. For instance, he worked on the Keystone Pipeline project. This was actually shortly after he began working for this company after getting his master's degree. He was offered this, like, hey, come work with me on this massive project, the Keystone Pipeline. So, you know, he was working in Washington, D.C. all the time because, you know, his reports were, you know, he was working with the lawyers for the Secretary of the State.
So what, on that point, just when you're on the trip, has there been a change in the student response to the stuff Andrew talks about, like the 100%. Societally relevant? Do you think students are more interested now than they were, I don't know, 5 years ago, 10 years ago, whenever, you know, you and him started doing the trip together?
Not necessarily. I wouldn't say more interested, but what I would say is they come away equipped with, okay, I really like geoscience, and now I know that I can actually do it for a living and actually earn a very good living doing it. And so they come away with that, which is so important because their parents don't have any idea, you know, and that has to be absolutely. I'm not ripping on that at all, but I think a lot of dinner table conversations have been had over, wait a minute, you want to go into geology or geoscience? What the heck are you going to do with that? You know?
Right. No, exactly.
And they come away with, I think, better answers for that.
Yeah, no, that's right. I mean, because especially, I mean, I got this a lot growing up in Michigan. What do? You look at rocks all day? And, you know,
that's what we do.
My answer now is like, well, I mean, kind of, that's what I do, my job, but that's not what most geoscientists do. And there's actually, you could go make a lot of money being a geoscientist too. And I think that's one of the very exciting ways, and this will come in later episodes. One of the really exciting things about the future of geoscientists is it's like, how do you make more geoscientists? Well, you produce a bunch of rich geoscientists. People look at that and they're like, oh, I can go make a bunch of money being a geoscientist. Like, okay, yeah, sign me up. Where do I sign, right? And I think that's true. We're just not very good at advertising that. But let's come back to this solutions at depth. Like, and we're just going to flip through a couple slides here that I put together for a talk a while back, but kind of convey this thing. And what do we mean by the impacts are on the surface? So there's two aspects to this, Chris. We talked about last episode. We talked about this event 4, the demand, the next peak demand for geoscientists is going to be big. We think that's going to be big for two reasons. One, the impacts are at the surface. And Chris, it's really interesting. We're seeing a lot of people getting hired in earth science departments, geoscience departments, earth and planetary science departments, whatever, you know, what used to be called geology is now called at various universities. There's a lot of, including at Penn State, a lot of people being hired in this kind of risk thing, geohazard risk. And it's really interesting work they do. There's a lot of like economics, a lot of social, a lot of modeling. And actually, these people who are in this field, this isn't me, but people who are in this field are really interested in, you know, students going into, for instance, the insurance industry. Because, I mean, we hear a lot about insurance companies, right? And with wildfires or all sorts of natural disaster type things, you know, insurance companies are in the news, let's say.
They need to have risk assessments, absolutely.
Yeah, and with people who understand rivers, who understand landslides, who understand, you know, this Earth system thing that we talked about with Lee Kump, like the Earth as a system. How are these things going to change in the future? Can we use the last 100 years of data or not? Do we need to take that data and up-model it, right, and say this is what it could happen in the future, the next 50 years, right? Like, that's the horizon that insurance companies need to be thinking about. So that's like a really important hiring pool, I think, for geoscientists who have these accessory skill sets that understand the Earth.
Now, Jesse, that probably looks like a consulting company getting hired by insurance companies, right?
I think it could be both. I mean, yeah, I think it could be in-house or environmental consultants, risk assessors. You know, I think this is an industry in flux, it seems like, and I'm not in this industry, so, you know, this is kind of secondhand information, but this is where Sorry.
That's the company. This is what Andrew's company does. I mean, they are an environmental consulting company. So that begs the question then, Jesse.
I think, Chris, let me just touch on that real quick. I think, the traditional view of environmental consultants is these are people who help companies navigate EPA rules, laws on the books. They help them navigate the process of getting approval to build something somewhere or to redevelop a former gas station or whatever. Like, they help them deal with the existing stuff. This future looking stuff, this forward looking stuff is kind of a different ball game. I think it's in the same category. And I'd be curious if, for instance, Andrew's company is hiring people who forward model risk like this or not. I don't know, but it's kind of a forward looking versus like get it done this year kind of an attitude. Anyway, sorry. That's okay. My question is then, and this is something that you and I've talked, at least on a personal level, a lot about, is what is the value of a geoscience degree versus an environmental science degree then? And because these are environmental consulting companies, and like we don't have data to show on the screen here to back up what, at least how I feel about it, but and I don't know, at the risk of maybe upsetting some people with this kind of statement, is that geology emphasizes the study of the Earth's structure and processes and solutions at depth. Right. Environmental science takes a much broader approach, encompassing the study of the environment and all of its interactions. It's a lot of this Earth system kind of thing. But what I come across when I look around online for this is that geoscience, somebody with a geoscience degree, whether that's a bachelor's or preferably a master's level degree, can do almost anything that an environmental scientist can do. But the opposite of that is not necessarily the case. Oh, yeah. So I think that's a really interesting point, Chris. And I think this is like, life advice kind of category. You can do whatever you want if you're exceptional, right? If you're just really good and you have an environmental science degree and you want to go do whatever, you can just do it. Like, I don't think there's anything that's like limiting you from being very successful with one of those degrees. It's just a question of like which one sets you up better for a given job. That's what we're kind of talking about here. And yeah, there might be more geoscience. The geoscience degree program, the typical one, might check more boxes in that way than some of the other programs. So that might add a little bit of clarity. But we'll talk to Andrew about this in an episode coming up here. But I mean, it's an interesting conversation. What degrees should you pursue? And I'm not sure if it matters as much as like the skill sets you're pursuing in addition to your degree. What kind of undergraduate research are you trying to pursue? Are you doing internships? Like, all those accessory things I think matter perhaps more than the name of your degree maybe, but I don't know. I don't know that to be true. So back to this like impacts on the surface thing. So, okay, the impacts on the surface. So we're going to need geoscientists to kind of help figure out what the impacts of those are and model those in the future, and all sorts of industries are going to need that. The solutions are at depth. This is the big thing for geologists. Like, we're talking about doing things in rocks and doing things to rocks at depth. And to me, Chris, this is a really interesting one. Like, depth is kind of the final frontier on Earth in a way. Think of like a geological map. We have a pretty good geological map of the United States of America. If you look at what's the app Rocked. Have you used this app before, Chris? Rocked, ROCK''D, I think it's called. It comes out of Wisconsin, this big geoscience data science research project, but it's really cool. Like, you download it and you can see all the geological features in your area. You look at the click on the rock unit, it'll pull up like a little bit of publications on it, but you look at that geological map of the United States and it's pretty covered. I mean, we have a lot of detailed mapping. There are some places that need more mapping for sure, but like, it's pretty well covered on the surface. I mean, would you agree with that? You go out into some pretty unmapped places like the Wind River. You mentioned that those are more remote and don't have as good of maps. But like, what would the application be of this app? Like, talk about that a minute.
I'm not familiar with it at all.
Oh, I mean, I just use it casually. Like, I just say, okay, what rock am I standing on right now? I get sometimes confused with the stratigraphy around where I live. And so, different ridges will be different units. If I'm on a hike, I'll pull it up and be like, oh, okay, yeah, I'm sitting on this
Okay,
whatever, sandstone
so
thing.
it just knows what you're standing on based upon where you are, so it combines where you are with the geologic maps that have already been established?
Yeah, it just pulls, from what I understand of it, it pulls USGS maps into the database, and also the data that is linked to the map unit. So if you're on the Tuscarora sandstone, you can click on it and it'll pull up a little bit of information about that, pulled from the publication, from the map database. So it's actually really cool.
Oh, that's
I
really
use
cool.
it casually just for, exploring. It's like you and me. When we used to go, this would have been amazing in our rock hounding days, going out in the Black Hills, and if we could just
find
be like,
the Unk Papa. That's
are
right.
we sitting on Unk Papa or not? Right? Yeah, exactly. So that, I mean, it's that, I use it for that kind of stuff. But
oh my gosh, we got you're right. We sat on the Minnetonka Formation a lot, and we're wondering, is this the Unk Papa?
This it? Which road did we turn on here? Yeah.
That's right. Okay.
So good.
All right. Interesting. All right.
Yeah.
Okay.
Well, I mean, it might
Jesse.
let me finish this thought real quick. As when we go down in depth, it gets a lot harder. Like our resolution as geoscientists of understanding the Earth, I think depth is kind of the final frontier. We don't know what's happening down at depth. Now, what does it require to figure out what's happening down at depth? Okay, drill down is one thing, and there's people who've drilled a bunch of places, but like not everywhere and not that deep. And it's focused mostly in pretty simple basins, which are still utterly complicated. So if I want to know what is the basement under you in Michigan right now, Chris, not many drill bits have gone down that far. So it requires tectonics, it requires geophysics, it requires structure, petrology, understanding how the continent formed, the tectonics of accretion back in time. Like that's a complicated problem, and we don't know a lot down at depth, especially in places that are not oil-rich basins. So depth is a really interesting kind of final frontier, I think.
That's right. And Jesse, I think like we should pick one of these solutions at depth kind of things and walk through it, right? Because we're looking at just some examples of solutions at depth. We're looking at resources at depth, like lithium, right? Or you pick your ore. What do you want? Lithium, copper, all these, the platinum metals. What do you want, right? Carbon sequestration. That's another solution at depth. Geological hydrogen is another solution at depth. And then geothermal energy. So let's pick one or two of them and go through an example of...
I mean, there's so much we could talk about. And I think probably the best way to continue, this is a big evolving conversation, but I hope we will do this through interviews with people. Lithium brines, extracting lithium directly from brines is a really important path forward. The Smackover Formation in Arizona, in Arkansas, is one of these like really popular places. The Smackover Formation, it's so good.
The McDermott,
McDermott caldera. So let's focus on copper real quick, because Chris, we've talked about this before. This is a big thing. Adam Simon, this is a while ago. It was a year ago now, more than a year ago.
I don't know. I'm not good at
Adam
that.
Simon on. Yeah,
I'm old. Everything was 30 days ago. So
is it pre-computer, post-computer? I don't know.
Okay. All right.
Adam Simon, he came out to give his. He talked about. He's done a lot of work on this, like copper as the artery for the energy transition. Like we need more. I forget what the statistics are, but we need more copper for.
It is the limiting factor for making the green transition. We just need so much copper. And so, Chris, this is we'll zoom in on this, but this is from Visual Capitalist based on some research by Benchmark Minerals. But basically, it's a really cool image that just shows this is only by 2030. So this is not that far into the future. The point is that we're going to need more mines is what they're after, more resource mines. So if we look at copper, the current supply is 22.9 million. There's an excess. How much additional supply we need by 2030 is 3.7 million tons. And you can go through these: nickel the same, graphite, lithium. A lot of these would be what we call quote unquote critical minerals or critical elements. But the important thing is we're going to need more mines. And Adam Simon has talked about this a lot. Like, we need more mines, but mines are getting harder and longer, taking longer to get initiated. So this is a really big societal conversation we need to have. Like, where do we want these mines to go? How quickly can we
get them online, because things like copper are needed for an energy they're needed at baseline, but it's going to especially be needed if we want this energy transition thing to happen.
We talked about this earlier, Jesse, with I think a number of that these rare metals are siderophiles. And so when Earth was differentiating, these iron-loving metals would glob onto the iron and just sink. And so these are, they just, some of them, but the point is that they get concentrated with depth. So we need to get better at finding these things, but also, correct me if I'm wrong, but we've just learned a lot about the concentration of lithium, and we're still learning this.
Oh yeah,
different geologic processes that concentrate these things, and I think there's a lot yet to be learned about the concentration of metals, and that's going to dramatically transform the landscape.
You are absolutely right. This is this is next episode. This is what we're talking about next episode. It's kind of a wild west here when it comes to things like lithium, rare earth elements, manganese, graphite, cobalt, like all these things that have been kind of moderate resources, but not like super high interest necessarily. And all of a sudden they're like, oh, we need more of these. We need to, reshore our supply lines, etc. There's a lot we don't understand about them, like lithium. There are a lot of companies starting up doing direct lithium extraction from basinal brines down at depth, and they're just sucking the stuff up, extracting the lithium, injecting it right back down. And this is actually a really promising path forward. I don't think anybody's solved it yet. Maybe a couple people think they have, but it's looking like it could be economical right now. And the Smackover Formation in Arkansas is one of these ones where people are focusing a lot of attention. So the answers are kind of at depth. For copper specifically, this is a really cool chart and an important one that Adam Simon spoke about this as well. But this is from research, again, by Visual Capitalists. I love what they've been doing on this topic, but this is in support, supported by BHP.
So what exactly are we looking at here? What's this graphic all about?
This is, since 1900, major copper discoveries in time. So time is the x-axis. Y-axis is depth. So as we go lower on this plot, the depth is at the surface. The top of the plot is at the surface. And the size of the symbols are the size of the copper deposit. And so the important thing here is to show that since 1900 till 80, something like that, most of all deposits were discovered at the surface. And now, since then, we're finding smaller deposits, and we're finding them at depth, 500 meters or even deeper. Some of them. Resolution is 1.5 kilometers down in the earth. It's a big deposit. So they're getting smaller and deeper.
Okay. Now I have a question for you then. All of these big copper deposits that were discovered easy because they were at the surface. Were these, what was the tectonic setting for most of these copper deposits that we discovered? It was related to rifting, right?
Well, no, a lot of these are copper porphyries, so they're some of the name, I don't know about all of these. I don't know the database here, but a lot of these are copper porphyry deposits. So, sitting above a paleo magma chamber, arc kind of related things. Think of Nevada, the Andes, things like that. So there's a lot of sort of older arc or accretionary type processes, I think. Most of these are copper porphyries, so there's a very particular, there's debate about the tectonic setting, but broadly arcs, I would say. But Chris, the thing, they're getting smaller and deeper, which means more expensive, which means harder.
Reminiscent, yeah. It's a lot like the petroleum issues,
Exactly. And so what is needed is to have people who come in and help do this better. And this is why AI will help perhaps, but AI is not going to solve this problem because this is a geological problem. We need to understand how the earth works. We need to understand how rocks evolve. Can we extract copper down from an active porphyry system? There are fluid redox gradients all over the place down at depth. We don't really know where they are, but can we extract copper directly from down there? If we could pinpoint, hey, there's a porphyry forming beneath our feet right here, 2 kilometers down. That's the type of thing that's going to be important and interesting in the future because we're going to need to keep finding these things. We need to keep extracting copper, and it's kind of I think an exciting place to be because it's a problem. And if you can solve the problem, it's a that's really good for you and for everybody else. So
exactly. So the takeaway is that we don't yet fully understand all of the ways that copper is concentrated. That's the next frontier.
That's the next frontier. And can we do it, at depth? We need to have an understanding of what's happening in our planet down beneath our feet. When we talk about this couple kilometers down in basins, we have a pretty good job because punched a lot of holes looking for oil and natural gas down in those places. When you get to tectonic settings where copper is forming, less so, right? A lot less so. So we need to kind of understand this a little bit more. And it's a really exciting time for people who are interested in solving some of these really big problems. And Chris, lithium, you brought up McDermott caldera. I mean, that's like in the last 10, 15 years, I'd say, has been kind of a game changer of understanding lithium deposits. This is, we know it occurs in pegmatites. You and I have been up in New England, Black Hills of South Dakota, these really like classic lithium pegmatite mines. I mean, they were mined for spodumene back in the day. That we've known about that.
I've got a fair amount of lithium in my yard.
You do.
Right
It
now.
might be a resource. Chris Boyce's yard might be the next resource.
I've got a lot of lithium.
That's true. Oh, that's pretty good. I mean, that's a well-known resource, and these brines have been extracted from, for a long time. Bring brine up, let it evaporate, extract the lithium out.
Jesse, hold on. I gotta go down memory lane a second. When we asked the owner of the mine for permission, and he said, "Go ahead, take whatever you want, Etta." Yeah. I'm not really sure he knew what he was saying.
No.
He didn't get a good look at the truck I had and the trailer that we were hauling, and
big F-250 with big utility
diesel pusher.
Trailer. Yeah. That was pretty good. Yeah. I have a big piece of beautiful spodumene. Yeah, and so good. I mean, it's cool. These are cool rocks, and I think that's why they're very fun to research and interesting to look at. But the brines in this volcano sediment packages, you brought up McDermott caldera, which is part of the Yellowstone hotspot track. I mean, is it which one? I forget which number in the sequence it is. Is it?
It's one of the oldest. Yeah, if not the oldest, it's one of the oldest.
The oldest. Okay, so, early part of this Yellowstone hotspot track, and this is a big lithium resource, but it's kind of volcano sedimentary. So big super eruptions, then weathering processes in this caldera generated lithium-rich clays in the subsurface there that are really lithium enriched, economic. And so 15 years ago, I don't think we really understood that clearly. And now there's a lot of focus on these types of tectonic settings. So this is just representing that the game is wide open. It's still, we don't know the result here. This is a wide open game, and I think it's really exciting when that's the case because sorry, go ahead.
It's the wild west of the geoscience world.
Yeah, yeah, exactly. We just don't know. I mean, there's so much we don't know about these elements. We know what elements we need. We know a lot about that, but we don't know where they are and where they occur. It's really interesting.
That's a really good point, that we know the elements that we need, but we also are going to have to push that envelope too and find acceptable alternatives to some of the like in the charging stations and things like this.
That's a great point, Christian. I've struggled with this in a research sense. From I'm taking the research program in a more applied, more socially relevant direction, right? And there's these decisions you have to make, like, what do I want to research? Where are there big problems? What's interesting? And what could I add value to my skill set and my research interest? And I decided lithium pegmatites, they're kind of interesting. I like the rocks themselves. There's some interesting problems in them. It's probably, I wouldn't guarantee it, but it's probably unlikely that lithium pegmatites are the mine sites of the future. That we need to understand these, just because lithium could be replaced by like sodium batteries, or grid scale there's like vanadium redox batteries. So there's technological stuff that's happening, and then we're kind of responding to that. But then the link is the resource, right? The link is the commodity. And so, it's massively in flux. But what's going to be required for all of these is people who understand geochemistry, who understand rocks, who understand broadly how the Earth works, how it did work in the past, tectonics, structure. All of these really traditional geology skill sets are going to be really, really useful.
And we're talking niche skill sets. Like,
yes, mineralogy.
I think that's
clay
the thing.
Mineralogy is very important for a lot of these things. Like, that's interesting.
That's one of the takeaways with this series, I think, Jesse, at least for me, is that if you're going to go into geoscience, I don't think you should be afraid to go niche. You know, to get down and dirty in whatever your passion is.
Get in the weeds, Chris.
Wriggle
down into the weeds and get comfy, because that's where the answers are. Right. And if you're down in the weeds in one place, you can, especially in my field, in geochemistry, in mineralogy, petrology, if you understand a phase diagram, really complicated phase diagram for the granite eutectic, if you understand that, you can think about problems in a thermodynamic sense when it comes to groundwater, when it comes to brine water fluid. You have like the toolbox you have, you can pick that up and move it over to another house and start working on that other house, because the toolbox is the same. And so I think going deep, and like really you have to go deep to develop that toolbox, to get other tools in your toolbox. Then you can use those tools in a variety of different ways, which is the thing that's really exciting to me.
Jesse, I just came, while you were blabbering there, I came to a conclusion. Okay, you know what I'm going to do with my geoscience classes is I'm going to I'm bringing in phase diagrams.
Oh, good. Okay.
I'm bringing it into my class.
You absolutely should.
I absolutely should. And it's not, I'm going to do this because...
So, Chris, hold on real quick. What you need to do is you need to bring a toolbox into your class, and everything that might be boring to them, have a wrench and label it phase diagrams and put it into that toolbox. Have something, geochronology on a screwdriver, write that, put it into the toolbox. Like, to really drive home this point to them.
That's a good idea. That's a good idea. You know what? I'm going to do that. I'm going to go buy a toolbox. Yep, I am. I'm actually going to do it.
Go into your garage. You must have an old one in there you don't need.
I can't get rid of my toolbox. I have to buy a new one.
Yeah. You probably need a tractor. Okay. You probably need some new attachment for your tractor for this too, I think, don't you?
Oh man, yesterday I was a working machine with my tractor.
Oh yeah, okay.
So good. Cut a lot of wood.
You got a real good workout there with your...
I did actually. I'm a little sore today actually.
Oh, is your seat not that comfortable?
No, you have to load the wood into the front end loader, into the bucket, Jesse, and that takes work. Okay,
poor Chris.
It takes work. So, all right, back on track now. Why am I going to bring back phase diagrams? Because that's a skill set that modern day students, and I'm sure that you see this too, they struggle with data, with looking at graphs, with looking at data and making sense of it. It's not about the phase diagrams themselves, but phase diagrams they're fun to make sense of. I think they are. It's like a puzzle, and figuring that out. So it just gives me an opportunity to make students look at data, look at graphs, and then make sense of it, and then talk about it from a geoscience perspective. So I'm going to do this. I absolutely, it's an opportunity.
I think that's a great thing to do, Chris, and because it is such, I think this phase diagram stuff is so important because mineralogy is going to become more important, and they're not intuitive. That's the difficult thing, is phase diagrams are difficult to understand. And this is perhaps maybe embarrassing for a geochemistry professor to admit, but I've thought I need to bolster my quantitative geochemistry skill set. I'm really good at understanding in a sort of a qualitative way. Like, I can look at a phase diagram and say, okay, it works like this. But when you start applying the math behind it to it, I need to bolster that skill set. I need to start working with some of these geochemistry programs a little bit more that are very quantitative, so that for my own value, right? And so I think I need to do that.
That makes sense.
Having high school students start to play those games is really would be really valuable for them. So
I think so. I mean, we're always being pushed at what skills are you trying to teach? What are you? It's not about the content. It's about a skill set. That seems to be the focus right now in our educational process where I work. It's all skill driven, not content driven. And so finding the balance between, because you need the content also, but we are definitely, people coming out of our school right now are they're lacking in certain skills, and one of them is definitely data interpretation for sure.
Yeah, interesting. Yeah, that's great.
Yeah.
That's,
all right. Anyway, Jesse, let's transition to another example, right? Can we talk real quick about another solution at depth example, which would be geothermal?
Chris, we have an episode on geothermal energy that I loved. I loved this episode, and this is probably the one that I recommend the most to people because it's such a fundamental thing. And I think people, like, you know, at all levels of knowledge, a lot of people are kind of like, well, why is the earth hot? You know, that's like a really basic question that I think people maybe just, they know it's hot, but they don't know why it's hot at depth. And so we kind of answered that. It's really interesting. Geothermal energy is a really, really important resource in the future. So I recommend that episode to people, like in normal conversations, talking about a geothermal heat pump at their house or something. Like, oh, we got a podcast episode if you want to like understand the science, or not the science behind the heat pump, but
everybody just got a little glimpse into a social gathering at the Rymank household right now.
Yeah, we're going to talk about, you know, what kind of heating unit you have in your house.
Jesse is just sitting in the corner of the couch there, trying to inject geologic conversations into.
That's exactly
normal,
right, man. You just got to tell everybody how important the earth is. So, but we have an episode on that, which is really great. But geothermal energy is a very, very interesting and potentially really important resource actually going forward. And so this is a map here, Chris, this one we're looking at. This is a map that just shows this is the potential where dark reds are high and light yellows and whites are low, the potential for deep enhanced geothermal systems, what are called EGS, enhanced geothermal systems. And basically all the red is out west in Colorado, in Idaho, Oregon, Nevada, Arizona, you know, Eastern California. Like there's a lot of red out west, right? And a lot of white out in where I live and where you live, white and yellow. Not a high potential for enhanced geothermal.
Hold on. First of all, define that a second. What do you mean when you say enhanced geothermal?
Yeah, good point. I'll skip ahead. Enhanced geothermal, this is fracking for heat. Think of it that way. It's just fracking for heat. So go down, drill down, frack the rock around it, inject cold water on one side, that water percolates through hot rock, you suck up the hot water on the other side, and you're taking the heat out. You're mining for heat, you're fracking for heat. So that's enhanced geothermal in a really basic sense. Go back to
hold on a second. I think you didn't do okay, I'm going to give you a little bit more leeway here. Okay, that we need to paint a better picture of this a second.
Of what enhanced geothermal is.
Okay. Once you went too short on the detail here for one time.
So the goal here is typically, I mean, as we drill down, we get hotter in Earth. That's universally
it's a geothermal gradient. Absolutely.
Geothermal gradient almost everywhere. Once you get past like a certain level, once you get past a couple hundred feet, it's getting hotter all the time everywhere. It gets hotter at different rates though. And that is to do with the geothermal gradient, the tectonics. Basically, it has to do with how thick is the lithosphere. How thick is that tectonic plate beneath you? The thinner it is, the hotter it is shallow. The thicker it is, the cooler it is deep, typically. I mean, it has something to do with whether the rocks are producing heat, whether there's a lot of radioactive rocks down beneath your feet or not. But the goal of this enhanced geothermal is find hot, dry rocks down deep that we can drill into, fracture the rocks, produce fracture networks, and then basically, in a really simplistic way, pass water or fluid through there that gets heated up, and then extract that fluid out and use it to drive a turbine to produce energy.
Okay,
or put
so
it
when
into
you
some
said
passive heat pump.
Put it in cold on one side, draw it out hot on the other side, you're just sweeping a lot of water through highly fractured hot rock.
Yeah, basically what they're after is looking for hot rock down deep and hot dry rock. But look at the temperatures on this plot. This is showing from the Forge project out in out west, where they're doing a lot of experimentation and testing these methods. What the goal is, you find a high geothermal gradient, meaning it gets hotter, shallower. That's what high geothermal gradient means. And we're looking at an engineered fractures that are 200 degrees C, 400 degrees Fahrenheit. So this is hot. This is water that will boil, and that's the point. You want to get it to the boiling point so you can drive the turbines and stuff, or you can use it to produce more electricity. But this is hot. This is really hot. This is a metamorphic rock. I mean, it's low-grade metamorphism, Chris, but this is metamorphism, and you're injecting water into hot, dry rocks. So
hold on. if you look at this map, then you're basically looking at, back to the map, where we're looking at the leading edge of the plate, of the North American plate, okay? I mean, it looks like, not a lot of high geothermal potential on the East Coast. That's the trailing edge. That's a passive continental margin. All the action is on the west because that's the direction the plate is moving. But then there's a bit of a contradiction, though, because the crust is thicker. The lithosphere is thicker there than it is in the east.
Well, actually, where all this heat is it's thinner typically. This is basin and range. So this is crust that has stretched by like 2 times. And so it used to be this. Yeah,
and now it's relaxing.
It's
right.
It's relaxed. You got this basin and range extension going on, thinned everything. Perhaps we've even lost mantle lithosphere beneath the crust. So there's hot rock upwelling there, and we get faults and we get hydrothermal features. I mean, all the hot springs and stuff are. You can look at these things on the map. Like hot springs are everywhere out west. We've been to a couple of them. And you can see the Yellowstone plume on here too, the plume track of Yellowstone. So there's a lot of stuff that is producing potentially really hot rock that's relatively shallow, which would be potentially good for this enhanced geothermal system, basically fracking for heat. And why is this interesting? Well, this is a pretty rough scale map. Again, like we need to know. If I skip ahead to this image, Chris, here, from the Forge project, like there's this opal mound fault that is running through here. Like there's basin fill mapped on here. There's granitic basement. This is a really simplistic overview. And if we want to know and do enhanced geothermal better, we're going to need higher resolution maps. And mapping at depth is really hard because it's expensive to drill. So any bit of like geology knowledge that we can add that provides higher resolution understanding of what's going on at depth is really valuable and will be really valuable for this important resource. And then again, this leads us into the next episode where we're going to talk about solutions in the rocks, but the solutions are at depth. I mean, enhanced geothermal is creating perhaps metamorphic reactions. This is a prehnit pompelliite grade or a green schist grade, metamorphic rock, especially when you add water to it. So it's a really interesting space that there's a lot of research and development going after because it could be a great solution.
So you're talking about changing the rocks by circulating hot water through them. They're already hot. Now you're adding water and you're going to cause chemical reactions. Is that what you're kind of alluding to for
right.
The next episode here?
Next episode. Yeah. Which is additionally an exciting.
I think it's super cool.
It's
absolutely
exciting.
Is.
There's a lot of potential for this stuff. But for this episode, we've sort of belabored on the point, but the solutions are at depth. I think that's if we come back to that, like the impacts of climate change are at the surface, geoscientists are going to be needed for that and are being needed for that. And a lot of the solutions are at depth. And so geoscientists, geologists, maybe even, dare I say, geologists, will be, I think, in high demand to help answer questions like
for
this.
Big problems.
Copper supply, commodity supply. Yes. Geothermal energy. We could go through a long list of these things.
We actually could. I mean, we just hit really on 2 different examples of solutions being at depth and how we need to learn more. And that's what geoscientists do. We study internal processes for Earth. And that's where the answers are going to lie. We think, for what's coming in the future.
Yeah,
to meet and to be on the front end of peak 4.
It's a very exciting time. I think it's a really exciting time to be a student, to be a graduate student or an undergrad even, and be thinking about these things. I think there are wide open spaces that nobody's doing much in, and it's a good time to be intellectually curious and get a good sort of background knowledge, and then go out and explore and learn and do great things. I think it's a really exciting time. So.
Yeah. Well, Jesse, I think that's a wrap. Is that a good place to end?
I think it's probably a pretty good place to end. I mean,
do you have a question for me?
I always have questions for you. Like, what have you been doing with yourself the last little bit? But Chris, how are you going to? What phase diagram are you going to teach students? What's the phase diagram that you'll use?
I don't know yet. So what I'm going to do is I'm going to take a phase diagram, which I don't know which one that is.
Have you done this before?
No.
Or not? No.
I just thought of it today. actually, when you were talking, I do that all the time. Actually, when you start talking, I start thinking about different things.
Chris, it's called tuning out. It's
being productive, though. I'm taking my time and I'm being productive with it.
You're like, okay, Jesse's going to roll for about 5 minutes straight here, so I got some time to get some thinking done.
Yeah. No, I think I think phase diagrams you just have to stare at them, and you have to orient yourself to the data set, and then I'm just going to invent questions about the phase diagrams, and I'm going to use this as like, okay, Professor Bullheis has been up here talking long enough now, go back at the lab and get with somebody, and I want you to work out this phase diagram. I think that I'm going to do that starting tomorrow. I got work to do right now.
Yeah, you got some stuff to do, man. Get on it.
I do.
That's exciting stuff.
Yeah.
Though. Yeah,
I think so.
I look forward to hearing how they handle it.
I still also have to give. Gosh, I can't remember. It was an episode a while back where we had a data set about. Gosh, what was
earthquakes? Number of large earthquakes?
No, it had to do. Oh man, I can't remember now. Anyway, I've got to go back a few episodes, and you wanted me to show my students this data set, but I didn't have them yet.
Yeah. No, I think it was something about. It was in that episode talk about. Is geology getting worse? I think we called it. But there are more earthquakes today than there were over the last 100 years. Is that what we're talking about? Maybe
could be. I don't know. I'll find it and I'll let you know. Yeah. I'll let you know what it is.
Anyway,
stay tuned.
Well, I think that's a wrap. Stay tuned for our coming episodes. We're going to keep talking about this theme, why it's a really exciting time to be in geoscience and the societal relevance of it. And I think it's an exciting time. You'll be able to go out and do great things and, maybe even make some money doing it. So I think that's a wrap. You can find us on all the social medias. We're at Planet Geocast. If you're watching on YouTube or Spotify, please leave us a review, a comment, a like, subscribe. We appreciate all that stuff. Try and get back to you. You can send us an email. There's a contact us link at our website, planetgeocast.com. Shoot us an email. We love getting that stuff. And you can download our Camp Geo mobile app, learn all the basics of geoscience in our free Camp Geo content there, plus some other audiobooks on geology of Grand Canyon, Grand Tetons, Yellowstone National Park, and a variety of other things. So download that first link in your show notes. We appreciate it.
Cheers.
Peace.